Okay, we're going to continue on here with chapter 14. We're almost to the halfway point here in chapter 14. It is kind of like the never-ending chapter. There we go. All right. So last time, obviously, we got into pretty much a conversation about salts, which we obviously did today in lab as well. Again, a reminder that when you're dealing with salts, which is really sort of the product or one of the products of a sort of acid-base reaction, you want to really look at the salt, which really should have a positive ion and a negative ion, and you want to decide if any part of that salt will go through hydrolysis. So the really things that we could use to help us determine whether or not the salt will go through hydrolysis is really where it came from. So once again, if either the positive guy or the negative guy originated from a weak acid or a weak base, then the answer is yes, it will go again through hydrolysis. And depending on, again, what it will act like, either an acid or a base, you will produce either H3O plus, which, as we've been talking about, you do need a Ka value, or you will produce hydroxide as a result of really that salt plus the water. Obviously, you will react with something else there or produce something else, but the main part in terms of the pH is you'll either see hydroxide or H3O plus on the product side. Remember that if these guys originate really from either a strong acid or a strong base, which is basically, again, group 1 and 2 on the periodic table, they will not go through hydrolysis. And essentially, they will be neutral in that case. So we had some examples this morning as well during lab that we did. And that's the key thing. We also talked about as well this morning, again, if you do have something that has the ability to really kind of go either way, either produce hydroxide by donating an H plus or produce H3O plus by by accepting an H plus or donating an H plus and making H3O plus, you do need to compare your Kb and your Ka values. And as we talked about this morning, you want to make sure that you are comparing the correct Ka and Kb values for those guys. As most cases, something like this has come from a polyprotic acid that has the ability to give away more than one proton. We also talked about that there could potentially be salts where both parts of the salt, like this guy here, could go through hydrolysis, as they both come from basically a weak acid and a weak base. In that case, you also would compare the Ka value and the Kb value for these two separate things and compare whichever one's larger is the reaction that it will do. We talked about a couple other ways to classify acids as Lewis acids or Lewis bases. Lewis involves electrons, and again, a Lewis acid is an electron pair acceptor. And a Lewis base, which we will see more of in later chapters, is an electron pair donator. It donates the electron pair. Any questions on that stuff we were talking about last time here? Okay, then we're going to kind of finish up the first half of this chapter here, talking about a little bit more how we deal with polyprotic acids. So polyprotic acids have more than one hydrogen that they could donate. So we have, again, monoprotic acids. Basically has one H plus it could give. Diprotic acids has basically two H pluses it could give, and something like triprotic acids has basically 3 H pluses a give. Again, an example of each of them: HCl, sulfuric acid, and phosphoric acid are all examples of each of these guys, right? When we do come to diprotic or triprotic acids, which are just commonly called polyprotic acids, the hydrogens again do come off in a stepwise fashion. They don't all come off at once. So we got, say, something like this guy here, which will lose 1 hydrogen and make HA minus. It would have a Ka value associated with that process. Then the next guy will lose a hydrogen, has a Ka2 sort of process associated with it. Is it easier to take off the first hydrogen or the second one? Which one's the easier one? It is easier to take off the first hydrogen. Yeah. First hydrogen is neutral. Then you're trying to take away an H plus for something that's negatively charged. It gets a lot harder. It gets harder and harder as you try to rip off all the hydrogens, more and more hydrogens. It gets harder to do so. This gives us sometimes what we think about these type of acids as like the overall reaction of just basically this guy losing 2 hydrogens overall. Make it here. All right, so when we look at polyprotic acids and we want to do some calculations, there's a few things that we kind of do when we do these type of calculations. So let's take a look at a table here, some of these values here. Very good, yeah. So here's a table. You have a similar table in your book of some polyprotic acids. And again, each of these K values that we see here in the table represent basically 1 hydrogen coming off at a time. The first K values for the first hydrogen, second K values for the second hydrogen, and the third K value there is for the third hydrogen, if there is one. So if we took phosphoric acid, for example, again, when we have phosphoric acid, which is a weak acid because there is a Ka value, the very first step that would happen is, again, it will lose 1 hydrogen. When it loses a hydrogen, there's still 2 hydrogens left. And remember that when it loses something that's positive, it becomes 1 more negative. And if we take the Ka value there, maybe from the table, it is 7.5 times 10 to the minus 3. The next thing that will happen is this guy here will then lose a second hydrogen overall. And that also has a Ka value of, say, 6.2 to the minus 8. And lastly, in the process here of phosphoric acid is this last guy. Here will then lose that last hydrogen. To make phosphate. And Ka3 value 4.8 to the minus 13. Yeah. It does. Everything in parentheses is aqueous. Bless you. Okay. So again, sometimes we do focus in on the overall reaction here, where again, this guy, I won't completely cross them out, but that guy, and that guy will all cancel each other out. And that leaves us overall, what's happening is really this phosphate in a stepwise fashion. Phosphoric acid is going to lose a total of 3 hydrogens and phosphate in this case. Now we see in these Ka values, what we were just talking about, what happens to the Ka values as we lose the first hydrogen to the second hydrogen to the third hydrogen? Ka values get larger or smaller? They do get smaller, right? The largest Ka value that we see there is actually the first hydrogen. And the larger the Ka value means more products, right? So that is where a majority of that H plus is going to come off at. When we get to the second hydrogen, that's a smaller value of K, which means we actually have more reactants, which means not a lot of it's going to come off in that step. And it gets even smaller here on the third hydrogen, which means we still have a lot more reactants at that point, which means even less of it is going to come off there in the third step. So it does progressively get harder and harder as you continue to take those hydrogens off to try to remove the next one. And again, that is reflected there in our Ka values. Question on that there. And again, as we were talking about this morning, if you had something like HPO4 minus or HPO4 2 minus in this case, you would have to find again one of the correct Ka values, one of the correct Kb values if you're looking at which way the hydrolysis reaction might go for that particular salt. In this case, you actually have 3 options that you would have to sort of narrow down from. All right, but let's take a look at an actual problem where we do some calculations here of, say, the pH and everything else involving, we'll use phosphoric acid since we just wrote out all those equations. So we'll do this problem here, and we'll come back to this pretty much. So in this particular problem, we want to calculate the pH of a phosphoric acid solution that is 5 molar. We also pretty much want everybody else involved there. We want the concentration of pretty much everybody, including the H plus. We have our 3 Ka values, and they obviously go with the 3 reactions that we just wrote on the previous page. So let's take a look at how we would approach this. So first off, the very first thing that's going to happen is that phosphoric acid is going to lose this 1 hydrogen like we wrote on the previous slide. And that will leave us H2PO4 minus. And that would go with our Ka1 value of 7.5 times 10 to the minus 3 in this case. So we're going to do an ice table here, and we're going to do an initial here, our concentration of our phosphoric acid. We're going to go 0 and 0. Change would be minus X plus X plus X. That means when we reach equilibrium, 5 minus X, X, and X. So very similar to what we've done before. Here we're just using our Ka1 because this is the first sort of step that's going to occur. If we write our Ka1 expression, it is our products over our reactants. And like normal, we're going to put our values in there. That gives us X squared divided by 5 minus X equals our Ka1 value of 7.5 times 10 to the minus 3. I'm going to assume that X is equal to 0 here. Give it a go. That's going to give me X squared divided by 5 equals 7.5 times 10 to the minus 3. I'm going to multiply the 5 to the other side and also take the square root of it. And that's going to get me 7.5 to the minus 3 times 5. A little square root action here. Going to give me an X value of 0.194, we'll call it. We do need to check it. So we're going to take our point, zero, let's try that again, 0.194. We'll divide it by 5, times it by 100%. And I hope it's good. It should be. There it is, 3.9%. That's a winner. Yeah. Original. I did the unhappy face again. Now we'll go happy face on that one. There we go. That is a winner. Used to not be a winner, and I had to do the quadratic, so I definitely changed the molarity on that to make sure it worked. So in this case, it actually did work. And after doing really the first ionization step here, where the first hydrogen came off, we actually have a bunch of answers for what we're looking for. So from the table here, we can see that the concentration of H plus equals X, which is 0.194 molar. We also see from the table that the concentration of H2PO4 minus will also equal X from here. So that is H2PO4 minus will be 0.194. And we also see at equilibrium that the phosphoric acid would be 5 minus X. So if we take 5 minus 0.194, we'll go with 4.81 would get us that. So we'll call it 4.81 molar. So from the very first ice table, we were able to get the concentration of this guy. We were able to get the concentration of this guy, and we're able to get the concentration of that guy. So that's not too bad. Any questions on that so far? All right. Well, since we do want the concentrations of some other things here, like the HPO42 minus, we will have to do the second sort of dissociation reaction here. So if we look at the second dissociation reaction that's going to occur, maybe. The second one that's going to occur is we got H2PO4 minus. We'll then lose the second hydrogen and make HPO4 2 minus. This is going to be our Ka2 value, which is 6.2 times 10 to the minus 8. So we're going to do an ice table here. Now, initially, we actually do have a concentration of this guy from the first ice table, right? So we do have some of that guy to start with. So our initial is going to be 0.194, which is the concentration that we see from our first ice table. What about H plus? Do we have any H plus from that first ice table? We do as well. It happens to be the same number, right? It happens to be 0.194. So both of these numbers come from the equilibrium line of the first dissociation that occurred. And this guy is going to be 0. Change here going to be minus X plus X plus X, which means when we reach equilibrium here, 0.194 minus X, 0.194 plus X, and X. Question on the table there. We're going to now put this into our second equilibrium expression, which again is our products over our reactants. So that is going to be our H plus, our HPO4 2 minus divided by H2PO4 minus. That's going to give us, in this case, 0.194 plus X times X divided by 0.194 minus X equals our second equilibrium constant, 6.2 times 10 to the minus 8. The assumption worked on the first one, so why not do it here? We're going to assume X is equal to 0. That is going to get me 0.194 times X divided by 0.194 equals 6.2 times 10 to the minus 8. I think I could do that. That is going to be X is equal to 6.2 times 10 to the minus 8. Once again, here we should do a little checking of our assumption. We should be good. 6.2 to the minus 8 divided by 0.194 and times it by 100 is not even 0.1%. It's really, really small. So the check here is good in this case, yeah. So this, yeah. Because if you get, the simple answer is if you get rid of all the X's, you have nothing to solve for. But the truthful answer besides that is what we're talking about here when we make the assumption is this. The change part is going to be relatively small, right, for all these x's. And the idea here is we're actually starting with 0 in this case for this guy, which means anything that you make, even if it's really small, is going to be significant, right? So if you had nothing, but you got a little bit of something, right, that's more than what you started with. So it's going to be definitely significant there, besides the fact that you would have nothing to solve for. But that's really why we don't get rid of that x. And that's why we only get rid of the x's that you subtract from something or add to something. And that's because you actually started with something. So the change is going to be relatively small compared to what you started with. But obviously, if you start with 0 and you make anything, it's going to be relatively significant. Yeah. Other questions? Okay, so from this table, we got another answer we could add, which is we could see from this table here that the concentration of HPO4 2- is equal to X. That means if we put it to our list here, the concentration of HPO4 2- will equal 6.2 times 10 to the minus 8 molar. Now, in this case, if we took our X value here and we put it back into the concentration of H plus and the concentration of H2PO4 what do you get when you take 0.194 plus 6.2 times 10 to the minus 8? You get basically 0.194 still. Yeah, it doesn't change all that much. Same thing with the first one. If you took 0.194 and subtracted 6.2 times 10 to the minus 8, you basically still have 0.194, right? So those concentrations really didn't change very much. As we've been talking about, that is the second hydrogen, right? A little bit harder, not as much is going to come off. So if we go back to our list here, we now could cross off this guy. That leaves us really just phosphate. And the only place where phosphate happens is in the third step. So we have to look at the third hydrogen coming off to allow us to calculate the concentration of phosphate in this case. And if we do that here, we'll do it on this one. The third step would be HPO4 2-. Again, losing the third hydrogen and making our phosphate, which is what we're interested in as well here. This is our Ka3 for our third hydrogen that's coming off, 4.8 times 10 to the minus 13. Once again here, we do have some initial concentrations that come from the previous tables. So initially here from the last ice table, we ended up with 6.2 times 10 to the minus 8. What about hydrogen? Do we still have some hydrogen from the last table? We do, and it's still that point, was it 194? Yeah. And we have 0 of our phosphate. So again, we got those initial concentrations from the previous step, basically. Change here would be minus plus X means that at equilibrium 6.2 times 10 to the minus 8 minus X, 0.194 plus X and X. Now that we're at sort of the third step here, we're going to go into the third equilibrium expression, which again is our products over our reactants. So putting in our values at this point, we got 0.194 plus X times X divided by 6.2 times 10 to the minus 8 minus X equals 4.8 times 10 to the minus 13. We've been doing good on the assumptions on this run here, so why stop now? We're going to assume X is equal to 0. Once again, it is just those x's as we were just talking about that we are subtracting or adding to something. So that would reduce this down to 0.194 times X divided by 6.2 times 10 to the minus 8 equals 4.8 times 10 to the minus 13. We're going to multiply this guy to the other side, come back through, and then divide that guy to the other side. And if we do that, we get 4.8 minus 13 times 6.2 to the minus 8, and then divided by 0.194. That is going to give us an x value here of 1.6 times 10 to the minus 19. Once again, we could check it by dividing by the larger number if you want, times it by 100, and we are nowhere near 5%, not even near 1%. So the check once again here is good. So the reason we needed to go to this third sort of ICE table here in the third step was because we were interested in our phosphate here. And now that we have our phosphate, we could add that to our list as 1.6 to the minus 19. And that will cross that off our list here. Also, if I was to add that X value back into here and back into here, would those concentrations change? They would not, because that's like a super small number, right? The minus 19. So again, not very much came off. So what we see when we sort of analyze going through each of the steps here and what is produced, we see that the amount of H plus that comes off, the majority of it came off in which step? The very first step, right? The very first step, we had a concentration of H plus of 0.194. Basically, we only were able to get off like 6.2 times 10 to the minus 8 in the next step, and even less in the third step, basically to the minus 19 came off. So the majority of the H plus will come off in the very first step of a polyprotic acid, because it gets harder and harder to remove the other H pluses as you go through each step. Which means if you have a question where it asks you to calculate the pH of a polyprotic acid and nothing else, you could pretty much just do the first ICE table, and you most likely will have the correct H plus concentration to calculate the pH from. Again, the only reason we really had to do step number 2 here in the third step was because we were interested in the concentrations of like all these other things right along the way. So we had to kind of go through each of those steps to get to those guys. But if it was just a straight question of what is the pH of the solution, we could have done the first ICE table, calculated the pH based off of that, and it would have been fine in that case. So again, in most cases, if you're just looking for the pH, polyprotic acid, do the first table, get the H plus, and calculate the pH from that. But again, if you're asked what the concentration of everybody is, you might have to go through each of the steps there to get to something like phosphate at the very end and stuff like that. So in this case, we could calculate the pH, which is the last thing that we're looking for here, which is minus the log of the H plus concentration. And again, we're using really the first step there, which is basically what it was all the way through. And if we do that, and it looks like 0.71 pH, pretty acidic. There we go. Question on polyprotic acids, how to work them there. Okay, so that is really the first part of the chapter here. All right, we're going to then roll into here second part of the chapter, which this is really kind of like part 2 of this chapter. So in this part, there's a lot of stuff going on, and we're now going to be entering in to really where the conceptual understanding of what's going on is really, really important. A lot of the calculations we're going to talk about, we have done before or will do, but understanding, what is going on is really, really important. We're going to be basically entering into buffers and titrations. So these are historically 2 of 4 things that give people a really, really hard time in this course, and it's that conceptual understanding of what's going on so that you do not do the wrong math. There's lots of places here where you could do a lot of math, but you shouldn't have done any of it because that's really not what's happening in the problem. So you want to really be careful here. So let's talk about, first off, really buffers. And to talk about buffers, what's really happening with buffers is what is sometimes referred to as the common ion effect. And the common ion effect is pretty much what the name sounds like. You have a solution and you put something else in that solution that creates an ion that's in common with what's in there originally. When you have a common ion effect that occurs, what happens is it will, in the case of a weak acid or a weak base, it will suppress its ionization, which basically means it will keep it together. So if we take, for example, we have everybody's favorite example, which is acetic acid, which is a weak acid. And if we have a solution of acetic acid, because it's a weak acid, it will break apart into H plus and acetate. So if we take a look at like the beaker that maybe we put this in, award-winning drawing here, we will have some acetate. And again, because it's that weak acid, it's able to set up the equilibrium, basically keep all these guys in solution, floating around. So let's say we had this weak acid in a beaker and we decided, in addition to the acetic acid, I want to toss in there a salt, maybe a salt like sodium acetate. So that is a salt, which means it is a strong electrolyte, which means it is not going to stay together. It is going to 100% break apart into ions, and it will break apart into a sodium ion and an acetate ion. So in solution, it's not going to stay together because of it being a salt and a strong electrolyte. It will make those ions. In this case, if I took this guy and tossed it into this solution, I am essentially adding more sodium ions, right? And I'm adding more acetate ions to that beaker, basically, when I toss it in there. Which ion's in common with the acetic acid is already in there? The ion that's in common is the acetate, yeah? The acetate ion is found on both plots, right? So when I dump sodium acetate into the solution, it being a source of sodium and acetate, I am essentially adding to this equilibrium more acetate. And our friend Le Chatelier's principle will tell us that when I add more acetate to this equilibrium, what should happen to the equilibrium? Should shift, in this case, which way? We added more products, which means it should shift away to the left-hand side. So by the presence of that common ion being in there, it's going to cause the equilibrium to shift to the left. And if it shifts to the left, what happens to my H plus concentration in this case? Does it go up or go down? If it shifts to the left, I'm making more reactants. That means I have less products, which means the concentration of H plus will go down in this case, yeah? And if the concentration of H plus goes down, what happens to the pH in comparison to just acetic acid? It should go up, yeah? So that is what it means when it talks about the presence of a common ion will suppress an acid from ionizing. It will push the equilibrium, bless you, to the left, which will keep the acid together, creating less free H plus. The result of that is, if you compare the pH to acetic acid to the pH of basically acetic acid and sodium acetate together, we will see a higher pH in the combination there of acetic acid and sodium acetate together than we would in just acetic acid by itself, because of the equilibrium shifting to the left. Question on that there. Okay, so let's take an actual look at this calculation wise to see this. So let's try this here. Why don't you first do part A? Calculate the pH of a 0.2 molar solution of acetic acid. The Ka value there is on the bottom. See what you come up with. So work on part A. Okay, let's take a look here at part A. So part A, we have 0.2 molar acetic acid. Has a Ka value 1.8 times 10 to the minus 5. And I know this is a weak acid, definitely because there's a Ka value associated with it. So this is just going to be a weak acid problem like we talked about earlier on in this chapter. So we're going to set up our equilibrium here with our acetic acid. It's going to break apart into H plus and some acetate. We're going to initially have 0.2 molar there, 0 and 0. Our change here going to be minus X plus X plus X. That means when we're all said and done here, we got 0.2 minus X. Actions of normally here, we will go into our Ka expression. I feel like it didn't write up there, did it? There it is. It was like dramatic pause, I guess, on the writing part. All right, it caught back up. All right, we're gonna go into our Ka expression here. There we go. All right, and again, that would be our products over our reactants. So putting in our values, we'll get X squared divided by 0.2 minus X equals 1.8 times 10 to the minus 5. We're going to do our assumption here. We've had a good run of it, so why not? Let's assume X is equal to 0. That is going to get us X squared divided by 0.2 equals 1.8 times 10 to the minus 5. Once again, here we're going to multiply the 0.2 to the other side and also take the square root of it. After we do that, 0.5 times 0.2 and square rooting it. Going to give us an X value here of 1.9 times 10 to the minus 3. We are going to check it, so we'll divide that by 0.2 times it by 100. And it's like 0.9%, so the check here is good. All right, so that means that if we go to our H plus here from our ice table, we will see that the concentration of H plus equals X, which means 1.9 times 10 to the minus 3 molar. That can now go into our pH, minus the log of 1.9 times 10 to the minus 3. And that gives us an opening pH here for our acetic acid of 272, looks like 2.72. Any questions on any of those steps? So that's very much just a Ka problem like we did earlier on in this chapter. So let's then take a look at part B of this. And in part B, what we're going to do is we're going to now have really the same acetic acid solution, but in part B to that solution, we're also going to add some sodium acetate to it. So let's take a look at those two things. So in part B, we got 0.2 molar of our acetic acid. And we're going to put in there 0.3 molar of sodium acetate. And obviously, since we have acetic acid there, we still have the same Ka value of 1.8 times 10 to the minus 5. All right, so out of these two, we definitely know acetic acid will set up an equilibrium. It's going to set up here the same one we were just looking at. Now, what about our sodium acetate here? Will that set up an equilibrium? It will not, because it is a salt and a strong electrolyte. So our sodium acetate will not set up an equilibrium when it goes for a swim, but it will break apart into sodium ions and acetate ions. So as we talked about earlier, the acetate ions here are going to be that common ion. So the sodium acetate in this case is going to be really a source of acetate in this reaction. That's going to affect the way that we do our ice table, because when we go to our initial, we have 0.2 molar of our acetic acid. We have nothing of our hydrogen. And the thing that most people miss on buffer problems, which really is common ion problems, as we'll talk about here in just a sec, they miss this part. And because in this solution, we do have sodium acetate present, it is a source of acetate to begin with, and we should have an actual number there. And that number would come from the sodium acetate's contribution, which would be 0.3. And that is because sodium acetate, when it breaks apart into sodium ions and acetate ions, it's a one-to-one relationship between sodium acetate and acetate, which means the concentration is the same for both of those guys. If I left that at 0 and did not do that, which is a common error that lots of people make, am I actually doing this common ion problem? I am not. I'm pretty much redoing the problem we just did, right? Which would be the weak acids. So it's really important to make sure that you have that number in the table. And again, if you don't do that, you're pretty much just doing the weak acid problem. The rest of the ice table here will be pretty much identical, obviously, to the one we just did. We're going to have a minus X, a plus X, and a plus X. And this will be 0.2 minus X, X, 0.3 plus X, which sometimes is also another common error that people make, is they're kind of used to, at this point, something being minus X, and they kind of automatically kind of roll with it. But down this side, it is going to be plus X in this case. This is going to go into our expression here. And because acetic acid is the only guy setting up an equilibrium, we will use, obviously, the Ka value for acetic acid in this case. So that'll be our products divided by our reactants. And putting those values in gives us X times 0.3 plus X divided by 0.2 minus X equals our Ka value, 1.8 to the minus 5. We are once again here going to assume that X is equal to 0. And that would reduce this down to X times 0.3 divided by 0.2 equals 1.8 times 10 to the minus 5. I think I'd much rather do this math here. So I'm going to multiply that, and then eventually afterwards divide that, right? So we're going to take 1.8 to the minus 5 times it by 0.2 divided by 0.3. Going to give us now an X value of 1, 2 times 10 with a lot of zeros. 1, 2, 3, 4, 1, 2, 3, 4, 5 looks like. This case. We're going to check our assumptions. So we'll take this, we can divide it by 0.3, times it by 100. And again, we're like 0.004%. So our check here is good. That means that, again, here from our ice table, X does equal the H plus concentration. So the H plus concentration is equal to X, which is 1.2 times 10 to the minus 5 molar. Going into our pH at this point, minus the log, 1.2 times 10 to the minus 5. Gives us a pH now of 4.92. First off, any questions on that there? Yeah. Because in part A, is different than what we have here, because in part A, there was no common ion. So we had just the acid by itself, which is going to allow more of that acid to break apart than it will here, because in this case, what we have going on is the Le Chatelier's principle. With that common ion there, it's going to keep the equilibrium kind of going back to the left there and not allow as much coming off. So they are different, the two, part A and part B, because part A, again, just a weak acid. But here we have that common ion effect happening where it's going to cause that equilibrium shift. And to sort of answer your question, we see the difference when we compare the two H values, right? If we look at the H value from the first part where we did not have any common ions, so really no common ion to start with, right? Point 0.9 to 3. Now, with the common ion here, our common ion, we ended up with an H plus value of 1.2 times 10 to the minus 5, which is much lower H plus concentration. And that's because the presence of that common ion, again, pushed the equilibrium back to the left and kept the acid together more than it did when the acid is just by itself. So it caused that shift to occur. And we see that in the H plus concentrations, and we also see it in the difference in the pH values as well. The pH of the acid by itself was 2.72, a much lower pH because it was allowed to let more of that H plus to come off than it did here with the common ion, where it kept it basically together, allowing less of that H plus to come off. The result of that is we saw a higher pH here, still acidic, but we saw a higher pH than what we had with just the weak acid. Yep. Other questions? So this is the actual effect that we were talking about. And when it says that the common ions present will suppress that weak acid from breaking apart, we see it actually here in these two calculations. We had much more H plus coming off with the acid by itself than in the presence of that common ion. And again, the result of that was we also saw a difference in the pHs of those two solutions. The weak acid allowing more H plus coming off gives us a lower pH to start with than here with the common ion. This is really what happens in a buffer situation, which is a common ion. This is actually a buffer right here, what we're talking about, but it's really the common ion effect. Now, in a situation where you do have this sort of common ion effect, which is really buffers, what we also see when we compare the concentration that we started with to what the equilibrium concentration is, was there a significant difference in the concentration? I'll get rid of some of my scribbles here. Was there a significant difference in the concentration of where this guy started with to basically where he ended up, and where this guy started with to basically where he ended up? And what I mean by that is if we took our X value here and put it into here and put it into here, the concentrations we would get for both of those is essentially the same. We would end up with 0.2-ish. I think you get like 0.19998, something like that. And here as well, you will end up with 0.3 at the end. So in situations where we have this common ion effect, because it's pushing that equilibrium back the other way and keeping everybody together, typically what will happen, and this is what happens with buffers, which are common ions, is really your starting concentration and your ending concentration pretty much going to be the same. And in those situations, you can do an ice table just like we just did there, but you actually have another option as to how you could solve that type of problem. And that other option is what is referred to as the Henderson-Hasselbalch equation, or David Hasselhoff, whichever one you like. But that is the Henderson-Hasselbalch equation here. And this equation is used for really common ion situations, which are buffer situations. And that is the pH is equal to the pKa plus the log of the base over the acid. So essentially, all the rest of it here is how we get to that equation. The pH equals the pKa plus the log of the base over the acid. And to calculate the pKa value, you take minus the log of the Ka value. You can use this for any type of buffer situation or common ion situation. So if we looked at the one that we just did, which is that 0.2 molar acetic acid with 0.3 molar sodium acetate. And once again, here our Ka value was 1.8 times 10 to the minus 5. We could use the Henderson-Hasselbalch, which is pH is equal to the pKa plus the log of the base over the acid, the pKa being minus the log of the Ka value. So if we did that, we would find the pKa value by taking minus the log, in this case, of 1.8 times 10 to the minus 5, which is 4.74. We could put it into our Henderson-Hasselbalch equation. pH equals 4.74 plus the log. Out of these two, which one is the base? I'll give you a big hint. What is the name of this guy? That's the acetic acid. So if I had to take a guess, that's going to be the acid, which means this guy here probably should be the base in this case, right? So in general, the base typically has like a spectator ion, something like sodium, something like potassium, something like that. Also, the acid typically has one more hydrogen because it's able to give away the hydrogen. So it typically has an extra hydrogen in it. So this is our base, which is what we want to go up on top, divided by our acid, which goes on the bottom. And again, if we put that in there and do it correctly, 0.3 divided by 0.2 times the log plus 4.74. That gives us a pH there of 4.92, which is the exact pH that we got when we did it with the ice table. So the way that we know that we could use this is you really need to have two things that are frankly related to each other. So you need to have two things that are really like a weak acid and a conjugate base, or a weak base and its conjugate acid. And that's really what we have here. We have acetic acid, which is our weak acid. And sodium acetate is really the salt of its conjugate base. It's really the acetate part here that is the relationship here, these two things. And it all really still goes back to the basic Bronsted-Lowry definition of acid conjugate base pairs. The only difference between an acid and its conjugate base pair, or a base and its conjugate acid pair, different of things are related to each other that you can use this. You will always probably have some type of spectator ion, like a sodium, a potassium, something like that, that will be there, but it's not really doing anything. It's a neutral salt as well. All right, so you can, in these situations, as we'll talk about, which are buffer situations, really common ion, you could use the Henderson-Hasselbalch equation, or you could do an ice table. It is really your choice as to whichever way you want to do these type of problems. I would probably recommend using the Henderson-Hasselbalch equation, probably less room for error, because again, very often people, when they do the ice table, they forget to do that initial concentration on the right that we were talking about there. So it's very common when people roll through the table, as we were talking about, that they forget again to put that guy in there. So with the Henderson-Hasselbalch, hopefully you won't forget to do that, since you need two numbers to do it. But you really can, as you can see, you get the exact same answer, regardless if you did it the table way or if you use the Henderson-Hasselbalch way. So now that we talked about the Henderson-Hasselbalch equation, and we're going to talk about buffers here in just a second, let's talk about how not to abuse the pour equation. Yes, so the pH is equal to the pKa plus the log of the base over the acid, where the pKa equals minus the log of the Ka value. So what I mean by this is, if you are to use this equation, it should only be used in a very specific situation of really buffers, which are common ion problems. So you really should only use this equation in really buffers, as we'll talk about, which are common ion problems. The problem that people have is they end up with two numbers and go, cool, I got an equation. I'm just going to stick it into the equation because I got two numbers. Why not? Let's give it a go. And you probably will get it wrong. So sometimes people overuse this equation because it's like, I'm not really sure how to do the ice table, or well, should I do the ice table, or whatever it may be. I'm just going to use this equation. So again, it's really a specific equation for a specific situation. It has to be really a buffer, which is a common ion type situation for you to use it. I personally would use this equation for all situations that are common ion problems and buffer problems. But sometimes people in books will show you a similar type equation. Probably should grab the right pen there. That also you could kind of use similar. The difference, though, is there is an equation where we don't actually get the pH, but we do have like a POH version of this equation. And the POH version of this equation is the pKb value plus the log of the acid over the base. So this one's reversed, and it is a pKb value. The pKb value is minus the log of the Kb value. There is actually also a really nice relationship between the pKa value plus the pKb value. It equals 14. It's kind of like the pH and the POH equals 14. It's the same idea. That's also sometimes useful if you maybe have a pKa value, but you need a pKb value, or vice versa. You could kind of calculate it really simply. So I put these up here. And personally, I probably will never use them, to be honest with you, personally, this version of it. But sometimes people will show it and use it. The reason why sometimes people will use this version of sort of the Henderson-Hausbach equation is for really basic situations, you know, when you have like a basic buffer or something like that. The reason personally I don't think you necessarily have to worry too much about it is because in most cases, you're asked for the pH, not really the POH in a lot of cases. So even if you use this equation, you still got to like subtract 14 from it, right, to get the pH value. So you might as well just stick it into the top equation there and get the pH right off the bat. But you can use this equation in really a basic situation, but you would still obviously need to subtract that 14 to get to the pH. So the nice thing about this guy here is it works for any situation. It could be an acidic situation, basic situation, neutral situation, it doesn't matter. You should always use it. So I would recommend to always use those set of equations. But again, if you see these are not wrong, but they are the POH. So you got to remember that's not the pH and get confused on that. So again, we want probably less room for error. And I would stick with kind of that pH equals to pKa plus the log of the base over the acid. Any questions on that there? Okay. So now that we sort of have been alluding to sort of buffers, let's take a look though, before we do at one example here. What is the pH of a stock solution of a solution containing 0.3 molar formic acid? That's what that is. And 0.52 molar potassium formate. The Ka value for formic acid is we got 0.3 molar formic acid. And we got 0.52 molar potassium formate here. These two things are related to each other, right? This is again the weak acid, right? And this really would be the salt of its conjugate base. In terms of the relationship here, the potassium is doing nothing but being a spectator ion, right? It is actually the formate here, right? Which is the sort of acid conjugate base pair, the difference of 1H plus that we have between those two. Because you could hopefully recognize that this is going to be a common ion. And once again, what's happening here is the formic acid is going to be the one that's going to set up the equilibrium. And it is this formate here, which comes from potassium formate, that's going to provide the common ion. So if you took the ice table approach, which you could have done it like we did the previous one. You could have done an initial concentration of 0.3 for this guy. You could have done a 0. And the important part here would be to make sure that you did have the 0.52 there. The change part here would be minus x plus x plus x. This would go down into 0.3 minus x, 0.52 plus x. This obviously would go into the Ka expression if this is the road that you chose. And that would give you your x, your 0.52 plus x divided by 0.3 minus x equals 1.7 times 10 to the minus 4. At this point, you could do your assumption, assume x is equal to 0 and solve for x like we did before. Check your assumption. Alternative to this is you could skip all that, right? And as soon as you recognize that it is a common ion problem, really like a buffer is really what this is as well, you could go right into the Henderson-Hasselbalch. So I'll put an R. You could do this. pH is equal to pKa plus the log of the base over the acid. Here we would find the pKa value by taking minus the log of the Ka, which is 1.7 times 10 to the minus 4. And if you did that there, minus the log, 1.7 to the minus 4, call it 377. And then we could go right into our Henderson-Hasselbalch with 3.77. We know for sure that this is our base, right? And that's going to be 0.52 up on top. Our formic acid obviously would be our acid. So we're going to do 0.52 divided by 0.3 plus a 377. Gets you about a 4.01 as our pH. If you did your X and you got to X and got your pH, it should also obviously give you the same answer. Again, it's whichever way you want to go. There's not really a wrong way. Either way is fine, but you just got to make sure if you did the ice table, you had that initial concentration of that 0.52. Otherwise, you would just be doing a weak acid problem. And obviously, you would get the incorrect value. Question on that there. All right. I think based on what we're going to talk about next, I think it's a good place to lay it up, I think, for today.